Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
How to database the two games, but it works. Probably you are familiar with Bordeaux mainly about the name of the wine, and Bordeaux now is clear to know. And probably after the conference, the Bordeaux will be much more known for its signal and image processing field. And before to start, with hard things, and I just want to say to show you a map, at the top of this slide, I know you have very strong background in geography, but sometimes just to relate. This is Europe, and this is France. Seattle is here, and now here is a French map, and Bordeaux is located. In the southwest of France. It's 3-hour fast train from Paris, 1 hour flying, and 2 hour driving from Spain. And this is the city of Bordeaux, and we have many small cities around Bordeaux, and the campus is located in one of them, which is called Talence, Talnec. And this is the different sub-region of the Bordeaux wine. So okay. And the area I'm coming with is the south, is this area of wine. It's called Grave or Pessac-Léognan. Okay. So now we will start. The idea of this talk is the following. I'm very interested to fit model with signal. Is my mind signal is not only covering the one-dimensional signal. So it can be image, and also it can be volume, or so that means that the title of my talk from 1D to the 3D. It's some kind of cruising, and I will recall some results which are supposed to be known by everyone from the basic electrical engineering courses. And the reason that I am reminding this because I will provide some input. Something new that can upgrade some very well-known idea. And they will do that for the 1D signal, for the 2D signal, and the 3D signal. In my mind, it's a certain kind of a continuum, starting from 1 to the 3D. It's not an easy talk, when you go from 1D to the 2D to the 3D. It's not always very easy for the understanding and also to extend the algorithm. So I will provide some I have been working for many years. Basically, my background, I used to work in control, then I moved to signal processing. And I have a strong influence from control, because people in control, when they want to control a process, they provide a model, and then they identify the parameter of this model. So this is the influence I had in the past, and that make me approaching mainly image and 3D process through mathematical model. Some of them you probably don't use them daily, but you heard about them. So that's the spirit of the talk. So my talk can be divided in 3 parts. Each one devoted, first one to 1D, the second one to 2D, and the third one to the 3D. And there is a connection between them, because we will use a very popular model in 1D and how it can be extended to the 3D and 2D and the 3D. And my purpose is also to show the limitation of this model. And in the case we can, provide model to answer to this limitation, I will do it. And I will show you what we have done. And when I see what we have done, the people I have the pleasure to work with them during the last 10 or 15 years, or probably more. So first, we will start with 1D case. with a very popular model in statistic or in signal processing in many areas, is the autoregressive model. And then I will remind you, I will recall two representations of the AR model. One is called the transversal one, and the other one is called the lattice form. And then I will raise, and if probably you are familiar with what are the limitations of this kind of model, the purpose, and always the purpose is how can be the model that we derive. We want this model that will be very realistic. Realistic, I mean, to represent the different kind of signal. That's, I mean, the purpose for everyone. So we want to fit exactly what the real world is. It's not very easy, but sometimes we make a lot of approximation. But we have to do it. So this is what I will mainly introduce, I mean, in this third part. And I will show you when it's necessary, I mean, to provide this kind of tool for real signal. Then the second part will be dealing with the texture modeling, texture analysis and texture modeling. I mean, how we can make analysis of texture, and are we able to derive model that can fit with different kind of texture? And in such a way, if we are able to do it, then we make also synthesis of image with this kind of model. And then I will probably derive something which is not very popular, but start to be known, which is called the Wold decomposition. And also some new result we have achieved very, very recently about this, the stability of this model. And then I will show you how the extension can be done from 1D to 2D. There is truly a gap going from this 1D to the 2D. And there is another gap from the 2D to the 3D. And then I will give some example. My purpose is not to go deeply in one application. My purpose is to provide you with some very generic models, and then people can use them in many kind of application. I just want to give one or two examples that we have been dealing with. So that's, I mean, the outline of the talk. With in the 1D case, if people in signal processing, they are interested to fit model with many kind of signal. The signal can be random, and they can. We will see and we will check that when we have in hand random signal, it's easy to fit the model. But when we have signal like this one, this is audio signal. If I zoom it, you can check that we have a lot of sine wave. This is this is real signal. It's an electroencephalogram signal. It lasts 1 to 2 seconds. And it appears when you are deeply sleeping. And this deep sleeping is called the paradoxal sleep. And you have some kind of sine wave. And the doctor said that this sine wave occurs because we have the neuron oscillating. The doctor said that, and they learn from the doctor. So when you record the signal, you find something like this one. This is a bird sound. And in the bird sound, you have also a lot of sine wave. So the question is how we can deal with this kind of signal. When part of this signal can be considered as a random process, and another part has to be considered as a signal which not exactly random, but containing periodicities, containing sine wave. So that's the problem. And now, before providing you with a solution to this problem, I will remind you some basic things about the AR model. Now, let us consider a 1D signal as a realization of the random process called Y, and with the order P. So standard form to write this is the following. That means the sample at time n is a concatenation of the previous sample weighted by the coefficient AI, and this coefficient is called the transversal AR parameter. And this is called sometimes the driving process. Y is existing because we have a driving process which is input. This is something which is known, but it just, yeah. Now we have, this is the time domain, and this is in the Z domain, and this can be, you can have, something with equivalent. This is a filter, and this is a random process with the input, and this is what's supposed to be the measured signal. And then we have to pay attention to that. This is something you know. But the reason that I am raising that, because I will show you how, if we extended that to t decays, many problem happens. And we provide with some solution to this problem. Now I will introduce something which is called the lattice filter with the reflection parameter. And and I will tell you some story and example that you are very familiar with, and probably you don't know that you are always, working with the lattice parameter in your pocket. So this is the model of our signal, and this part is called the predictor part of the signal, and this is the error. If you want to predict this signal, you can do it with this part, and this can be considered as an error. In one hand, it can be considered as an error, and in another hand, it can be considered as the driving process. So, many work has been done how to estimate this parameter, and you can do it, and by minimizing this kind of error, and then you obtain a set of linear equation, and the solution of this linear equation. This linear equation are also called the Yule-Walker equation in 1 decade, and there is a lot of work that has been done, and the reason for that is mainly the following. This parameter as the correlation parameter, and this is the A parameters, and the problem is to inverse this R matrices, which has sometimes very nice properties, to get the parameter. So, if you invert the R matrices, it costs about n cube arithmetic operation. But in many occasions, the R matrix has some very nice structure. It's a topless structure, and then you can decrease, the computation cost till n square. So this is something which is very well known. Now, and to do that, there is an algorithm, and this algorithm called the Levinson algorithm. Now we will introduce something different. I state that the A parameter is called the transversal parameter. And for instance, if we increase the order by 1 unit, now we obtain new parameters. And when you increase the order and when you estimate the parameters, this one, the A1 obtained with the order P, and this one, the A1 for the order P plus 1, are different. So that means when you increase the order, all the parameters change. Have in mind this. Now I will introduce the basic ideas to have the Levinson algorithm running. It's based on the following idea, that you consider the signal as a two wave. One is a forward wave, another one is a background wave. And the result will be two different signals interfering. And this idea, now, for instance, if I have, n sample, I want to predict this one. This is what we call the forward prediction. And then we get an error. And this error is called the forward error prediction for the order P. But we can also predict in this way, when we rank from the present to the past. And then we will introduce the backward prediction. And we predict this one. If we know all this one, we can predict this one. And then we introduce a new error, which is called the backward prediction error. One can demonstrate that there are some relationship between these two errors. And with some mathematical computation, the purpose is not to provide all the mathematical derivation, but just to rise and to extract some ideas. So we can easily show that we have this kind of relationship between the error, the background error for the order P, and the backward error at the previous order. And this relationship holds, and we introduce a new parameter. It's called rho of P. This parameter is called the reflection coefficient, and sometimes is called the lattice coefficient, or also the Parker coefficient. We now have in hand two different representations. Sorry, we'll be back. We have the previous one with the A parameters. This is the A parameters they are here. And now we are raising a new parameter called the rho, and I named this parameter the reflection coefficient. And there, when you derive the Leibnizian algorithm, you get this different kind of equation. And this one is very, very interesting, because it states that the variance, when you estimate the parameter at the order P, is equal to the variance with the parameter at the order P minus 1. And this variance has to be positive. This one is positive. That means that rho, the reflection coefficient, has to be less than 1. And store this remark in mind. And the derivation of the Leibnizian algorithm lead to this complicated relationship. This relationship states that for any value m from 1 to p minus 1, so that I have p parameters, I have this recursive relationship between the A parameters and the rho parameters. And there is a recursion to get the one from the other. These are the classical transversal parameter, and this is what we call the reflection parameter. The nice properties of these parameters are all the lattice parameters are less than 1. And to check the stability of the model, you just have to check that rho is less than 1. And when you have a model, and when you stop, for instance, at order 1, you get the parameter rho 1. And when you increase the order, you get the rho 2, rho 3, rho 4. And all the previous parameters you have estimated stay the same. But when you deal with the transversal parameter, if you increase from 1 to 2 or from p to p plus 1, all the value of the parameter change. So that means Now I go ahead. This is, I mean, a diagram that can represent the way of the sample are moving when you change P to P minus 1 to P. And you always get the same diagram from order P minus 1 to order P. This is how you make the implementation when you use the lattice filter. And this is very convenient if you want to make an implementation on a chip, on a silicon chip. Because, I mean, you use the same frame, only the parameter change. And this idea has been used in many applications. The first and very popular one has been used in the 80s by TI in the first chip dedicated to speech analysis intensities in a very popular device, which is called Speak and Spell from TI. It has been translated in many languages and used by kids to learn. You show images and for animals of everything, and then the machine spell the thing. And this was one of the first applications. The other application, there are many other. The other application is in the cellular phone. The device, the algorithm used for the data compression in the cellular phone is based on this representation of the signal. And these coefficients are sometimes also called the Schur coefficient. So this is, I mean, some kind of a resume about what I said. When the model order increases from P to P plus 1, the first row parameter is not modified. However, all the transversal parameters has to be adjusted. That means that they are modified. So it's better to work with this one than this one. Another idea is we can easily check the stability by using the row parameter. The AR is supposed to be stable if and only if this parameter is less than 1. Now, this is also, sorry, I will show you the first slide, or probably the second slide, this one. You know, if the model is stable, that means that the zero of this polynomial are inside the unit circle. It's very easy. I mean, when the order of the polynomial is a little bit high, it's difficult to check if the zero are inside or not. But when you extract the row parameters, you have a formula, and it's a recursive formula to check, to compute, I mean, the row parameter, and to check very easily in a recursive way. So you can do it by the computer. So everything what I recall now is known. Now have in mind this result. In the second part, I will extend this result to the 2 decays. Now, another problem. If I go back to my AR model, to my signal, this is a voiced speech. The voiced speech is a speech dealing with vowels. For instance, in all the languages, in all over the world, speech can be divided in 2 different kinds of speech. The voiced and the unvoiced. The voiced, we have periodicities in it, and the unvoiced, you have just, it can be considered as a random process. When you close the mouth, you pronounce a consonant, and it's an unvoiced. And when you open, I mean, the mouth, it's a vowel. So how to deal with this kind of signal when you have periodicities? The other question is, if you want to do it with the standard AR model, you fail because you miss the information about, I mean, the periodicities. And we introduced it. A much more complicated model, not much more, but I mean this kind of model. These are to be considered the A parameters, and the B parameter has to be considered as, in the previous part of my talk, as an AR, are modelized by an AR process. For instance, A is given by this AR model. B is also given by this model. This is what usually people in signal processing do when they want to have this kind of model. But what is new here is we know that we have sine wave in our signal. But these sine waves are not fixed, they move. In a certain sense, they are random. So we pay attention to that, and then we will be considered that the A parameters and the B parameter will be modulated by sine wave. And then we obtain much more, I mean not complicated, but model that pay attention to these periodicities that are contained in our signal. And we have exercises this model in different kind of signal. And for instance, when you have a rare signal like the signal I showed you earlier, then A and B appear truly they are not constant because they are modulated by the sine and the cosine wave. And this is the idea, how to modelize the signal as a non-stationary signal containing, sine wave. If you do it with the basic idea, one frequency has to be considered as a constant. And if you do it with this kind of model, then this is what you obtain when you make the spectra. For instance, if we have a signal like this one, the A parameter we extract are the following, and the spectrum will be here. So we have something much more realistic, to make analysis of the signal. And we also exercised that. This is the technique how to do that, and I wouldn't want to pay attention to that. Now, this signal, this one, this is also a real signal. And as I told you before, this is the EEG signal, and not the standard EEG, but it's an EEG that lasts few seconds during the paradoxal sleep. And for instance, what is the interest of this signal? The doctors are interested by this signal because if you make analysis of the signal, you can check the quality of the sleep. For instance, when you get some kind of pills, some kind of medicine, this signal disappears and you have a flat one. And this is supposed to be one of the indicators of the quality of sleep. But first you have to check when it appears. It's a problem of segmentation. And when it appears, you have to extract the different components of the signal. And with this kind of the model, you can do it very easily. And we provide the result to the doctor, and they use it, for different kind of application. You can do that. You can make analysis of the signal of this model by the standard AR model, because you miss all the periodicities in the signal. Now, I show the limitation of the one, the teacher people, when people are teaching, they always want to make some kind of resume that to be sure that the main idea has been raised. So the main idea is we have limitation of the AR model in the 1D case, and mainly when we have to deal with signal which are random, but also they have some periodicity. And the problem is how to fit a realistic model. This is also, I didn't say it, but the case in the radar and the many things for speech, and when you deal with speech. Now there are many models of speech for coding or for synthesis based on this kind of model, which are sine wave and random process. Now we continue our cruise, in the 2D case. These kind of images are called the texture, and they are extracted from very popular book and album, which is called the Brothers Texture. And the first series, this one, and this one, can truly be considered as random. They appear. There is no periodicities in this texture, and we can consider them as a random process. This one, there is some kind of periodicities, and they can be considered, image with periodicities. This one, they have not exactly periodicities, but they have some kind of structure. This one also, this one. So how to deal with the different kind of texture? So, you can divide the different kind of image in 3 series. The first one have a stochastic aspect, random aspect. The second one, you have some periodicities, and the third one, it doesn't look like a random process. It doesn't look like a periodical process, but something different. But you have some directionality. This is if you have the wood and you cut it in the longitudinal way. This is what you get. Now we will provide with some models, and if we have a digitized textured image, it assumes it to be a realization of an homogeneous field. The equivalent of the homogeneous field in the 1D case is a stationary, if you have a stationary signal. Now, in this case, you tell homogeneous field. And we will try to fit an AR model, but a 2D AR model. Now we will state that this image can be modeled by this kind of model, which is an extension of the AR model from the 1D case to the D case. And then we will introduce the transversal parameter, this one. So now we'll go a little faster because there is a different way, different way of scanning the image. When you have 1D signal, it's very easy. You know what's the present, what's the past, and what's the future. But for an image, it's difficult when you scan it. It's not natural to say that this is when you are dealing with this pixel, that this one is the past or it's the future. It depending. You can scan it from this way. You can scan it from different kind of way. This is a difficult problem to handle with image when you are dealing with model. So there are different kind of way of doing it, and these different kind of way are coded by this acronym. So there is something equivalent to the 1D case, what we call it the Yule-Walker equation, and in this case the A parameter as a vector, and the toplex matrix, the component of this toplex matrix are also toplets. This one is toplets, and all the set is toplets, and it's called topless black toplets. It's a little bit complicated, but there are many solutions to this problem. So there are many solutions, but you have to estimate this parameter, and there are many approaches that has been derived to estimate, and so we did This is a book when we have many results regarding this matter, and some papers that appear in the transaction of signal processing and in 1996 and a few years ago dealing with this kind of this problem. If you have some interest, I can provide you with copies of the paper. Now, what we did, due to the fact that the lattice filter have very, very nice properties, with my student and some of my colleagues, we extended the lattice filter from 1D to the 2D. And this, the cell I show you in the 1D case is similar. Sorry, I have to start again. The cell we obtain in the 2D case is similar to the cell in the 1D case. This line means that this is a vector, and we are now dealing with the raw coefficient, as I called it before. They are the reflection coefficient. We call them K, and they start to be matrices. So we can then consider the image as also, I mean, two-wave images, like in the 1D case. And with one of my previous students, who is now professor in the Peking University, Liu, who derived this very complicated thing, is now professor and head of the department in the Peking University and used to be my PhD student. We derived this algorithm, how to extract, how to derive in a recursive way these parameters. So that means we have in hand something which is very similar to the 1D case. We have in hand, like you have in hand in the 1D case when your cellular form, when the lattice parameter ran, we can also have in hand in the 2D case the lattice form. So when we got this parameter, we then said that one equivalent representation of the AR model in the Z plane will you get the I mean the filter can be representation with the H, Z1 and Z2. In the 1D case, you just have Z1 or Z2, but just one, not two. But in the 2D case, you get something like this one, Z1 and Z2. And you can write the polynomial like this one. It's a two-variable polynomial. And in this case, it's very hard to test the stability of this polynomial. We have not an interest about the stability in itself, but we have interest because I have an image, I fit a model, and I want to check if the model is stable or not, if I can simulate in a computer or not. That's my purpose. So if you want to do it, it's difficult to test the stability of this one. And the stability can be stated, and it's called the BIBO. That means bounded input will provide you with a bounded output. Otherwise, the system is unstable. If you have a bounded input and the output can start to be infinity, the system is unstable. So it's something you can understand very easily. And this means that you have this kind of relationship. Now,
Professor Najim,
yes?
Could you please tell me what is exactly the stability in the last equation? I mean, in the 1D case, you test the 0 points.
Yeah.
Basically the poles.
But in this case, you know, you are not in one plane. You have the balls, and inside this one, you have to test and to check if the zero are inside or not. And it's not easy because you can make a factorization of this polynomial. You can make this factorization. And what I want to show, how we can extend it, the result of this one from the 1D case. Sorry, I have to be back. This one. You know, in the 1D case, it's very easy to test the stability. You just check that this parameter you can compute at every time, at every stage is less than 1. And the idea we had is, can we find something equivalent? Because we extended the lattice filter from the 1D case to the 2D case. We obtain new bodies. Can we do something which can be equivalent to that? That's the idea. That's the idea we'll explain now. And to check if this hold or not is not very easy. So then we go back to our, we extended, as I told you, the lattice form to the 2D case, and we obtain this kind, the error that raised in the 2D case, we call them the forward error at order M, and we have this kind of relationship, which is similar to the relationship in the 1D case, but these are matrices, and these K parameter are matrices. So now we are dealing not with scalar parameter, but with matrices. And we call this parameter the reflection, the matrix reflection coefficient. And sorry?
What's the shift in the 2D case? You have like S minus 1, but I'm not really sure what that...
What is the shift?
Yeah.
The shift. So I will be back later to the shift. I will just state the theorem and then we'll be back. Okay. I will answer to your question if I answer. I will in this part, there are two different things. The new idea is how to go from the 1D to the 2D case. Extending the lattice filter from 1D to the 2D case. So when I move from 1D to this day, I obtain these matrices. They are called the K matrices, which are something equivalent to the reflection coefficient in the 1D case. But now we got some matrices. And these matrices, I think probably it's better if I go back. For instance, suppose that I scan the image, or this one, for instance, this one. It's not a non-causal way to do it, but I don't care. You know, if I have this pixel, with the 2D AR model, this pixel is considered, I can predict this one is I know the neighbor of this pixel. This is the meaning of the AR model. The AR model means that this pixel is, you get the very close pixel in a D domain, and you have to define what will be the D domain. It's called the region of support, and you weight in a certain way the very close pixel for it. So, and you have to choose different kind of domain, you know. This one is called the quarter plane, you know, a different name. And this one, if this is the past and this is the future, this pixel, I mean, is obtained, is predicted with all this one. And if you say that it's the past and the future, it's a non-causal way of doing things. But this is a causal way, and this is a causal way. And then you can define, if you estimate this one by only this part or this part, different kind of error. And the error that appear in the 2D case are something similar that what you have in the 1D case. I think I start that before you arrive. I think when you have a signal, you can say that you can predict this one according to the previous sample. You can, if you do it this way, it's a forward one, and if you do it, it's the backward one. This is the current one, and there is the previous one. And then you define the backward and the forward. But in the 2D case, it's much more complicated because you can define 2, 3, or 4 errors, depending on the way of you are scanning the image. So it's a little bit more complicated. And then instead of obtaining, scalar parameter, you obtain matricial parameter. So now if I go back, sorry, I have to move from to the 2D case, and when I get when I get the lattice models, these equations are not similar, in the way of writing them they look similar, but in the 1D case this is scalar. In the for image, these are matrices or vectors.
So what's the dimension of those vectors?
It depends of the domain when you scan. It may be 3, 3, 4, 4, 4, 4, 4 times 4. The dimension of the matrix. If you choose the model of order 2, it will be 2, 2, order 3, 3, 3. You can increase it, but usually it works with 2 or 3. 2 times or 3 times. So the idea we want to check is having in hand this reflection coefficient, can we extend the Schur-Cohn test? Remember, in the 1D case, the Schur-Cohn state that the parameter rho has to be less than 1. Can we extend this to the 2D case using this parameter with our matrix parameter? This is the question we raised, and we try to answer to this question. And we try to answer, and the first answer, we were unhappy about the first answer. Because, and I will tell you exactly the story, how is it, because I think we have time, because we have 1 hour and a half time. And I will tell you the story about that. We wrote the paper, I think probably in the year 2000. And in this paper we state that we now provide an extension of the Schur-Cohn stability for the 2D case. We submit the paper, and then we receive the review, and the review said that's a nice idea, but please make simulation in this case and in various cases. And we make simulation, more simulation that we have in the paper. And then we find that this is what we provide in our paper is only a necessary, but not a necessary and a sufficient condition. That means you can use it for a stability test. So we have been unhappy about that. And we discussed with mathematician people, and the mathematician people said, no, that's a very nice result, because when you can demonstrate that it's only a necessary, it's a result. So you have to submit again your paper. And we submit again the paper, and the paper has been accepted. But we're still unhappy because about what we claimed at first, that now we have reached a new result. And this has been published, 2 years ago in the Transaction of Information Theory. But we continue to work. And I have the chance that I work with 2 young mathematicians, and they come from the operator theory area, and we extended very, very recently. The result is not yet published, and we never presented it at any conference. I just talk about it in a seminar I gave in Princeton, and the second time, but it will be now published in a journal. It's accepted to be published, and it's a lot of mathematics. And just want to tell you that now we have reached a new result with the necessary and sufficient condition with this kind of model for image. But it can also extend it to multidimensional things, and it based on the way that mathematician people call the slice function. I won't deal with it because it will be too long. And I mean, this will be in the paper, in this journal, Communication Information System Journal. It's especially so dedicated to one of my colleagues, Professor Thomas Kylot from Stanford, from Stanford, and I will attend next Thursday a seminar dedicated to this event, and this journal will be available. So now I close. I'm in the window about the stability. We moved from 1D to the TD, and we extended this very popular test of stability. And now we will be back to the texture. We have different, slots in this talk. And now, for instance, we have been dealing with the AR model, and now we will check if we can modelize this image, this texture with the 2D AR model. So we will start with the 4-4 model. That means the A, I, and G. G will move from 1 to 4, and J for 1 to 4. And now we estimate the parameter. And now we try to make a synthesis of the image. When you work with the image, you can check very easily just with your eyes. This is what we obtain. We try to fit the model, we estimate the parameter, and now we make a synthesis. We find this one.
Question?
Yes?
So what domain did you use for that synthesis analysis?
What do you mean by domain?
The quarter plane?
Yes, a quarter plane, yeah. But it doesn't depend of the domain you order. It's what I want to show. What you get doesn't truly depend. There's something we miss, and what I will show that how we can deal with this component we miss. I will introduce a new concept, and I will. That I mean, I want to also go further. It doesn't also depend of the order. You can choose order 2 or much higher order. You never be able to make a synthesis of an image if, and you only if use the AR models. That I want. This is what I want to show.
But one other question.
Yes, please.
What kind of noise were you driving that with?
Noise. It's what I will be explaining. You can use white noise or different kind of noise, but you never get, something realistic. It's what I will explain now. So now, if you get a spectrum, fast Fourier transform, you get this kind of spectrum, and this kind of spectrum, raise question, because you check that in your spectrum you have lines. But now if you check the spectrum of this model you have synthesized, you check that you have something which continuous, that you still have some line. That means you have some structure in your spectrum. But how you can deal with structure? What kind of model will give you, the explanation of this structure? Now, if you extract, when you have the model, you fit, when you have an image, you try to fit a model, and then you have an error. And if information remains in the error, that means that the model is not very accurate. And in this case, if we make analysis of the error, this is the error. I can check with my eyes, but there is still information appearing in the error. And if I make a spectral analysis, I check that they have lines. So that means that I have missed something. Now, I will give some other example, and they will give the answer to that, how we can solve it. This is another. Now, this image is different from the previous one, because this one is completely random. This one is completely random. The spectra can be considered as a continuous spectra. There are no more lines. So that means that in this case, if you have this texture, and I can make a synthesis of this by using the AR model. But I can do that with this kind of texture. That means there's something missing. And this thing which is missing, now we have to introduce what they call the Wold decomposition. Sorry, before presenting this one, I will go a little bit. I have better slide. Have to find it. Yeah, this one. To be much more clear, I have to back, forward, and then I will be back forward. Yeah. Forget the N and forget the T. Forget the N and forget the T and forget the N, forget the. There is a theorem. This theorem has been stated, I think, in the 40s. And it states that any stationary, the 1D case, any stationary process can be decomposed into two parts. The first one is completely random, and the second one is a deterministic part. Where in 1D case, and the theorem states that the purely random parts can be modeled by an AR, autoregressive model, or by a moving average. But they don't give any information about the deterministic part. But all the people use to derive models. For instance, remember the signal I show, I mean the EEG. In the EEG, it doesn't, fit under the theorem. It fits under the theorem because there is a random part and some part you can predict. But you always only use the AR or the EMA model. That's the reason that you fail. In the 2D case, you can, from a very naive way, say that if you extended to 1D to the 2D and forget that I have no T, I just N and M, it can be decomposed in two components. One is completely random, and another one is a predictable one. If you do that, you are wrong. Why? Now I have to go back to my. In a pure journal math, these people, Hellstrom and Lausnanga, they demonstrate early in the 60s that any 2D discrete random homogeneous random field can be uniquely represented by the following orthogonal decomposition. In this decomposition, when you have a stationary random field, an image, for us, they don't care. These people, they don't care about the image. But later, we care with the image. This 2D stationary random field can be decomposed in the two parts. One is completely random, and another was, we will call it deterministic field. But deterministic in a complicated way. This deterministic field is itself decomposed in two parts. One is a completely deterministic, and we will call it the harmonic one, and another one is a mixture of something deterministic and random, and it's called the evanescent field. Then, to summarize, in 1D case, I have just 2 parts. But in the 2D case, I have to deal with 3 parts. One is completely random, one is deterministic, that means it can be it can contain periodicities, and another one is called the evanescent field. So if I want to make synthesis of image, I have to modelize the image with these 3 components. First one, second one, and third one. That means in the 2D case, you have 3 components. And what the people in math, pure math, demonstrate that this one, and this one are orthogonal, each one to another. So that means you can work independently with this one, and this one, and this one. So this is what the pure math provides. And then the texture field, so, sorry, there is a mistake, is a superposition of 3 orthogonal fields. The first one is completely random. The second one is a deterministic one. And the third one is a new one. It has been introduced. The root of this one is in pure math. And if you are able to provide model for this one, and this one, then you can make good synthesis of the image I showed you earlier. And now if you go to this is called the 2D Wold decomposition, and it involves the decomposition of the spectrum. Because we have 3 orthogonal, then you can separate, the spectrum into 3 independent parts. The first one is dealing with the random part, this is with the harmonic part, and this one with the evanescent part. The first part is absolutely continuous. In the 1D case, when you have a random process, the spectra is continuous. When you have sine wave, you get the Dirac, and this is a singular spectrum. And you can provide model for each of the components. And for the random part, you can use something like this one. This is very popular. It's the AR models. For the random part of the image, you can use this kind of model. For the harmonic part, you can use sine and cosine. And later, one of the people who worked a lot in this area is Yossi Frankos. He's professor in Beersheba in Israel, and he worked with some other people, and he proposed in the mid of the 90s and early in the 90s this complicated model. This model states that the evanescent field is a sum of various evanescent fields, and each one can be modeled like this one. Don't pay attention to all the parameters. They mean the following, that this one is modeled by the AR model. This is also an AR model. And each AR model is modulated by cosine and sine. It's like I show in the 1D case, but it's more complicated. And S and T that appear here are an 1D AR models. And this parameter that appear here are some frequencies. And the idea is to check, first to extract the evanescent component and to fit and to try to test and to estimate all these parameters. It's not an easy task. And Frankos has proposed, now before going to the mathematicals, inside, now I will give some image. This is completely random image, and you can check that but you can check that the spectrum is completely continuous. This is an harmonic. I mean, you have periodicities, and when you check the spectra, you get dot. I mean, but this is a spectrum. You have singular spectrum. Now this image is different from this one, And you check the spectra, if you compute your spectra, you get something different. You get lines. Lines is the representation in the spectrum domain of what we call the third part, first part, second part, third part, which is called the evanescent. Why the name of the evanescent? The name of the evanescent doesn't come from physics. It comes from math when the people say that in 1D case, the measure of the evanescent component is 0. That's the reason that we have just 2 components in the 1D case. Now we can go ahead. In this texture, I know that we never get a model with only using the 2D AR model. This is the spectrum, and what I want, I will go a little bit faster. This, if you model by a 2D AR model, you can only extract the random part of this image. And if you want to make synthesis with that, you never obtain the original image. But if you want to reconstruct that, you have to pay attention to the evanescent one. And if you get the model of the evanescent one, then you can use it, and this is what you obtain with this when you use this third part. I have some other example. Remember, in the first slide, when we only use the 2D AR model, when you try to modelize this texture, this is what you obtain. But now we obtain that. We obtain the following. Sorry. If we make analysis of this original texture using this Wold decomposition, we can now reconstruct this image, and this is what we obtain. It's completely different of the first one we obtained using the 2D AR model. So that means now we raise the limitation of the 2D AR model. They can only synthesize or modelize a purely random image. When you have image that looks like random, then you can use them. Otherwise, you have to use this, the 2D, the Wold decomposition. And for instance, this is the wood, it's called the wood texture. This one is very hard to get, the synthesis of this one. And if you extract, the evanescent component, then you can synthesize this image, and this is what you get. Also for this kind of image, this is the original image, and this is the synthesized image. You can, but now what I didn't talk about it, that's the mathematical computation. The first algorithm to estimate the evanescent component has been derived in the mid of the 90s, 95 or 96. But it's a very complicated one. It's based on the maximum likelihood, and it takes some time to converge. And we derived in my group, an algorithm based on some geometrical approach that can extract all the evanescent composite one after the other one. And it will be published it has been published in conference, and it will be published in some journal in the next forthcoming months. And I work very closely with Professor Francos. Our graduate students make a lot of comparison with so the method we proposed is more efficient and more robust, more rapid to extract this component. Now,
so you mentioned this geometric algorithm. Are these, basic, the concept is try to analyze the spectrum, get one of the evanescent component out, and then try to analyze the rest of the spectrum to see if there
the algorithm is based on the following idea. If you get the map of the plane, and we are interested in extracted lines, because the spectrum of the evanescent component is line, is how to extract it. It's like to extract it one after the other, the lines. And there is an arithmetic result on the Fari series that give you that you have a finite number when you cross the map about this. And we use the mixture, the fusion of this number set of possible lines with some geometrical consideration, and then we can extract with this technique all the components in spite of using very complicated maximum likelihood. So it's based on some geometrical approach and the map of the spectrum. You make running your algorithm, you extract the spectrum, and then you have to find some clever ideas to extract the lines. That's the ideas of the. Now we crossed from 1D to the 2D case, and we raised many problems. And the group I am working in, we have for the time being strong interest in volume in the 3D case, and so we have strong interest on providing models. So the volume can also be considered as a realization. A volume can be considered as a realization of a 3D zero-mean homogeneous stochastic process. This is a synthetic block of image. And this one is a seismic block. What do we mean by seismic? You are not probably, you know, or I don't know if you know, you can have an image of the underground by, like the image you use with the echography, when you go to the doctor and you make echography. And the echography now come from the idea of seismology, The people in the oil industry, they try to have the map of the underground, and then they can make analysis and to check if the area where they can find oil or not. So, and then the application for everyone is the echography, when the doctor can check how the organ are or not. So this is something completely artificial, and this is a block of the seismic block of image. And our purpose is to try to fit model to this kind of block. I have just 5 minutes and I will. So in the 1D case, the Wold decomposition, just M, no N, no T. And I just showed in the 2D case that we have each homogeneous field can be decomposed in 3 parts. It's what I stated before. The completely random, the harmonic one, and the evanescent one. And now in the 3D case, it's more complicated. This new result has been demonstrated in pure math that in the three-dimensional case, if you want to make analysis, or I mean, you have to deal with 4 components. One is completely non-predictable, it's a random one. The second one is containing the periodicities, it's a harmonic field. And then you have to add 2 different bodies, and we call them the evanescent of type 1 and the evanescent of type 2. So that means, and this result is not coming from algebraic simulation, it's come from operator theory that states in the 3D case you have 4 components, and this 4 component is orthogonal each one to another. So that means it's very easy to fit model to each one. So this will be published, I mean, in the pure journal of math, which is called the Journal of Multivariate Analysis, probably at the end of this year, which is a generalized multidimensional world decomposition. The first author is a pure math people, Flavius Turcu. And so that means, now if we have, in the 3D case, this is a voxel, not a pixel, you know, it can be considered the voxel, and it can be decomposed in 4 and only 4, no more, but no less. Sometimes it can be less if you have no periodicities. But I mean, the maximum of component is one is completely random, one is harmonic, and then you have 2 different kind of things that are the evanescent field. And we fit, I mean, different model to each one of these components. Now in the spectrum, in the spectral domain, you have also 4 components. These have singular value because the first one is the harmonic, and the 2 other one are the evanescent one, and this one is completely random. And this is an example. If I have a complete random process, it looks like something completely random, then it can be exactly modeled by a 3D-AR model. And now we have been also dealing with some side order problem, and mainly how to estimate the order of this. This has been done, and and it's about to be published in many conferences or journals. Now I will skip this. I will skip. Too complicated. Now another example. When I pay attention to this volume, I check that I have some kind of periodicities. Now if I go from the time domain to the frequency domain, I find something familiar, like in the 2D case, that I have dots. So the spectrum have singular value, and this is easy to represent, and I can represent it by this kind of model. Now, this is the model we construct for one of the evanescent component. This part is modulated by a cosine, and this one is modulated by a cosine, and S and T are 2D AR models. And this is what we get. And the other component is like the following, but in this case, S and T are 1D AR model. This has been demonstrated and it works. And now I'll make some simulation. For instance, this is a volume. If you pay attention, you can say that this one is stochastic. It's something, it looks like the image I showed you early in this talk. And when you go to the spectral domain, you find something like this one. You have a plane. This is a non-random parameter, but in this area you continue spectra with a plane. So that means in the evanescent component you have a mixture of something which is random and something which is not random. So this is a little bit complicated to imagine. And now I go a little bit faster. If you have this kind of image, this kind of component, then you just have lines, I mean for the spectra, and I will go faster.
I think we have the room for another 3 minutes or so.
2 minutes, yes, yeah. So I just want to know, now if you have this kind of volume, and if you get this kind of spectra, and you know that in spectra you have something which continues and something which not continuous. And we used it recently, and it works, the high order statistic. And if you use this high order statistic, you can completely clean, I mean, the spectra, and you obtain something like that. This is what the algorithm gave. And for instance, if you use this kind of high order statistic, this is the volume, and you have mixture of the spectrum. You have random part, and you have deterministic part, and you can completely separate the two different ones. And now just an example. And if you have a volume, and in fact I am interested in some seismic volume, you can separate the deterministic part and the non-deterministic part very easily with this kind of approach. And this is a seismic block. This is an artificial view, it's not natural. And this is the deterministic part, and this is the undeterministic part. And you can use, I mean, to clean, to enhance, to make volume enhancement, I mean, to extract what is interesting for you. I'm sorry, but I have finished. And in the last, I mean, you have some references in different paper that appears, which will be appearing. And you have a copy of my slide, so if you have some interest in it. And now I just have some advertisement. I'm the co-chairman of this conference to be organized in Bordeaux with some colleague from the US, and it will be in Bordeaux next month. And another one, also I will chair it with Professor Sanjit Mitra from Santa Barbara, to be held in next March. No, sorry, it's 2006, not 2005. There is a mistake here. Okay, if you have a question, I don't know if you can roam that, I will be happy to answer.
Okay, thanks a lot, Professor Najim, for your excellent talk. I think we don't have the room for too much time. But if any of you guys are interested to talk to Professor Najim, please come to basically send me an email afterwards. I can surely squeeze a slot inside. Well, I guess other people need to use the room.
Sorry. Okay.
This is Phil Chow.